29. I am pleased
Good day everyone! So by the way, I am Rhea Bacolana, and for this video, we are going to explain and discuss the application of abstract algebra in group theory and its application in robotics, computer vision and graphics, and analysis theory, together with my productive groupmates. So here we go!
Hi everyone, I am Ralph Lawrence Weaver.
And I am si Joy Argisal Oga.
Hello everyone, this is me, Maika K. Amargan.
My name is Rhea May E. Baxal.
So let's start!
When we're at school, everything we learn is separated into subjects: English, physics, math, and in some schools, even a technology class. But the truth is that everything is related. We might have noticed that technology is everywhere these days, and the same is true of abstract algebra. In practical life, the idea of groups used in abstract algebra has helped civil engineers and scientists to find areas and volumes of complex structures, and conducts and gathers research to further knowledge in a particular area, make hypotheses, test them through various means such as statistics and data, and formulate conclusions based on the evidence. In this lesson, we're going to go into more detail about the application of abstract algebra. Let's first define the word abstract algebra. Abstract algebra is one of the most important bodies of knowledge that a mathematically educated person should know at least at the introductory level. Indeed, a degree in mathematics always includes a course covering these concepts. Used in computer science in the development of algorithms and software for working with mathematical objects. It is also used to design formulas that are used in numerical programs and for complete scientific computations. Unfortunately, abstract algebra is also seen as an extremely difficult body of knowledge to learn since it is so abstract. Algebra provides methods for organizing and structuring knowledge so that, when applied to technology, it allows scientists and engineers to produce systematic, reproducible, and transmittable knowledge. Analysis, design, modeling, simulation, and implementation then become possible as efficient, well-structured activities. Abstract algebra can help with understanding what's going on under the hood with linear algebra. Group theory provides the basic framework for understanding how to manipulate the expressions involving non-commutative matrix multiplication. Abstract algebra seems to be one of area of mathematics virtually crying out for computer instructional support because of the availability of multi-representational tools and appropriate software that can be used to bridge the existing gap between the concrete and the abstract. In the abstract algebra, group theory studies the algebraic structures known as groups. The concept of a group is central to abstract algebra. Other well-known as algebraic structures, such as rings, fields, and vector spaces, can also be seen as groups endowed with additional operations and actions.
One basic question in robotics automation is how to describe contacts between solids to a robot. For example, how would you ask a robot to put a cube in a corner? Well, one word for that is symmetry. We apply the label symmetric to anything that stays invariant under some transformations, right? Symmetries have long been used to describe a certain object or appearance of an object, a scene or a set of symbols like language or musical notes, etc. Now, as we all know, group theory is a mathematical theory of symmetry. The group theory helps us to understand symmetries. When we are dealing with an object that appears to be symmetric, group theory can help with the analysis. This is a powerful tool that has a direct impact on research in robotics, computer vision, computer graphics, and in medical image analysis. Later on in this video, you will be able to know of why and how will this course of abstract algebra can really be applied in such field of science and technology, which are in robotics, computer analysis, etc.
This course addresses both a real need in graduate education and in research communities for using formal methods in symmetry, asymmetry, and near regularity. Symmetry is a pervasive phenomenon in both natural and man-made, including biological environments. Humans have an innate ability to perceive and take advantage of symmetry in everyday life, but it is not obvious how to automate this powerful insight in man-made intelligent beings such as robots. On the surface, symmetry is simple and basic. In essence, the concept of symmetry is much more than a mirror reflection. Rather, it can span a continuous spectrum of multidimensional spaces. We argue that reasoning about symmetry can likewise play a crucial part in the advancement of artificial or machine intelligence. A computational model for symmetry is especially pertinent to robotics, computer vision, and machine intelligence in general, because in these fields we're studying how a man-made intelligent being can perceive and interact with the chaotic real world in the most effective way. Recognition of symmetry is the first step towards capturing the essential structure of a real-world problem and minimizing redundancy, which can often lead to drastic reductions in computation. One fundamental limitation of computers is their finite representational power. One simple floating point error can destroy any perfect symmetry. One's ability to tolerate departure from perfect symmetry reflects one's level of sophistication and perception, which needs to be built into the development of machine or artificial intelligence. While a compelling mathematical theory of symmetry has existed for more than a century, very few computational tools prevail in recognizing and taking advantage of real-world symmetry. One cause of this shortage is the discrepancy between the ideal algebraic formulation of symmetry, namely group theory, and the instantiation of symmetry in the noisy physical world. We have developed a computational framework that can effectively treat real-world symmetry as a statistical departure from regularity. The final goal of this course is to build perceptual systems that can recognize imperfect structural regularity or symmetry while discriminating subtle pattern differences.
The development of inexpensive and fast computers, coupled with the discovery of efficient algorithms for dealing with polynomial equations, has enabled exciting new applications of abstract algebra. Abstract algebra in a group theory and its applications in robotics, computer vision or graphics, and medical image analysis shows how tools borrowed from these fields can be efficiently employed to solve relevant problems arising in robotics, computer vision or graphics, and medical image analysis and theory. Abstract algebra and geometry are a necessity in robotics. If you are designing a robot for a specific task, you will be tailoring its design to that same task. You will need to find the correct size parts for your robot. For example, you might find yourself with parts provided and need to ask, how big are these wheels? You will then use your geometry skills to find the area, circumference, or maybe volume. Or, while most wheels may be circles, others may be other shapes for different tasks, such as climbing stairs. What shapes are the best to use as fingers, and how do you calculate their size? Also, a lot of robots have turning and rotating parts. You're going to have to understand angles and the way the different rotating parts affect the movement if you want to make a good robot.
Measurement. If you are going to build a robot, you will need to know how big your robot should be in order to perform its task. If you want it to pick up a basketball, then you need to measure the ball so that you can be sure if its hands are big enough for the grip to be secure. That is measurement in action. You also need to know how to do unit conversions, as you will likely find yourself measuring in a variety of units. If a part comes labeled using centimeters but you learn to know what size it is using inches, you can put your conversion skills to the test. Combining geometry with measurement is absolutely necessary for designing and building your robot. Next, we have statistics. So you build a robot, where you should test out how well it performs. Maybe your robot moves at a certain speed and you want to see how fast it moves. After a couple trials, you have some data. But now what do you do with that? This is where understanding of statistics is important. You might want to find its average speed from the trials. Maybe you want to see how fast your robot moves different objects of different ways. You could build a data table and then graph the results to better see the relationships between weight and speed, or perhaps you want to see the standard deviation to make sure your data is consistent. All of this requires a good understanding of statistics. Then abstract algebra. Last but certainly not least is algebra. You may only be just starting out, but this is one of the most important parts of math you will learn if you want to do robotics. Abstract algebra is essential both in basic and more advanced robot making. Algebraic thinking involves finding the patterns and relationship between different things like speed and power, or wheel diameter and distance traveled. And when you get into more advanced robotics, you start using more and more algebra as you incorporate the physics of what is happening into your understanding. You will use algebra in finding the relationship between speed and distance and time, or force and acceleration. But don't just take it from me. Here's what Bill Nye, or the science guy himself, has said about the abstract algebra.
I'm curious, because I'm considered things. And it turns out that algebra is a single present here of whether or not you will pursue a career in science and engineering.